Welcome back friends for another session on quantum field theory and quantum entanglement, and we have been looking at elementary QED process in the process trying to compute them essentially. In the earlier lecture we have looked at Baba scattering. So, Baba scattering which is essentially a process in which a pair of electrons and a electron positron pair interacts with each other. So, we have drawn the diagrams essentially of the Baba scattering. The Baba scattering is you have essentially two diagrams, electron. So, we chose the time as this and a positron coming together giving rise to an electron positron pair. Okay. This is called the S channel or the annihilation diagram. The other one would be, so E minus goes to E minus, E plus goes to E plus, and they exchange a photon. So, this is some sort like a T channel. So, this is in which there is no annihilation which is happening, but this is E plus E minus going to E plus E minus anyway. Again time in this direction. So, then we also so when does the annihilation you can look at this just statistics, I mean the amplitudes of this process, and accordingly you can compute the entire cross section and so on, so which has been left as a exercise. There are several features of this Baba scattering associated with this, which will be addressed. Okay, let me not overstate it. Okay, let me just say one or two features of the Baba scattering will be asked in the essentially in the assignments. We will be asking you in the assignments how will you proceed essentially. So, this is about Baba scattering. We also looked at molar scattering in the previous exercise, in the previous lecture. So, molar scattering is E minus go into E minus, which is essentially a T channel and a U channel process, because we have same states, same initial states and some final states. So, T channel, and you can also have the corresponding one here. Okay. So, we call this as P1, P2, P3, P4. And the time is always this direction. Okay. So, this two process we had it done this in the previous scattering and the previous lecture. So, this is the T channel and this is the U channel. These two scatterings we had done. Now, let us look at other two scatterings or other 3 or 4 scatterings and their amplitudes. The other ones are essentially in the list we have written are Compton scattering. So, here it is a process of electron photon going into electron photon. Okay. So, here this is interesting actually, this this is a very interesting result, which has also a non-relativistic limit and various things essentially, which is well studied in already quantum mechanics also. So, let us first draw the diagrams. You have electron going in, electron propagator, electron coming out. So, this is in the photon coming in and the photon going out. So, you have P1, P2, this is the time direction, P3, P4. Then you can exchange the momenta of the outside, the P1 and P3. So, you have a U channel diagram, or okay. So, you can draw this diagram now in this fashion. Okay. Okay. So, this photon is not wiggling properly. So, okay, let me draw it again. Very good. So, this is again P1, P2, P3, P4, this electron coming out, coming in, and this is time. So, the propagators essentially. So, this is the incoming electron. So, this is the incoming electron and this is the outgoing electron, a photon. Okay. The electron incoming and outgoing are clear, but the photon picture is slightly. So, your the P2, the electron with momentum P2 interacts with P3 instead of P1, or P1 interacts with P4 instead of with this thing. Okay. Now, you can work out the amplitude like always. Essentially, one can work out the amplitude. So, we have U bar P4 I e gamma mu by. So, we just have to see this is T channel. So, this is T channel, this is U channel. So, the momentum exchange would be P1 minus P2 square P1 minus P2 square minus ME square P1 plus P2 plus ME on the numerator, and then U of P2. Then this covers the entire lower part. You also have the epsilon of the final states essentially. Okay, epsilons mu of P1 and epsilon nu, and there is a second vertex okay, I gamma mu, I gamma nu. Okay, here I missed the second vertex. P2, sorry, P2. And then you have epsilon nu of P3. Good. So, this is the amplitude for the first diagram, and similarly you can do the same thing plus P1 to P3 in the second diagram. You replace P1 wherever P1 comes with P3, and wherever P3 comes you have to replace it with P1. So, this is P1 minus this is fine, this is fine. Okay. Now, this is the various interesting features of the, this is the amplitude Im of the Compton scattering. Now, you can sum over the initial states and take the average over the final state spins, and you get a simple formula which relates to which in the massless limit so you essentially take ME goes to 0. So, this gives you something like m square averaging over all the spins and everything is equal to e power 4 s by u minus u by s, or you can okay. Now, on this is the simple result. Okay, this is the average over the spins of all the fermion of all the electrons, and this is what you have a simple formula for. You can write it in terms of T also. So, this just becomes e power 4 for 2T square by SU, right, T is SU, right. So, this gives you this formula. So, you see that now you see that the formula is simple in the massless limit, but in the massive limit it is a long expression. It's actually a long expression. Now, you can work out the m square, but there is also this non-relativistic limit which is called the Klein-Nishina result. Okay. Results for the full massive form. So, if you take ME not equal to 0, you get a completely invariant form which is very complicated, and this is expressed in terms of the Klein-Nishina results for the full mass form. Then there is the non-relativistic limit which is the Thomson scattering and so on, so essentially. Okay, very good. So, now with this let us move to the next cross section. The Compton scattering is very important, you know, it is the scattering which tells you when the relativistic effects are important. Okay, it is the it gives you something called sets the limit when relativistic effects are important in a scattering process. And so, this gives in terms of some frequency wavelength essentially. So, wavelength is equal to, it is called the Compton wavelength, which is equal to given by h cross by mc, where m is the mass of the scatterer essentially. So, what is the mass of the scatterer, and this is the change, lambda is something called the Compton wavelength. So, below this wavelength for the given the mass of the particle or the scatterer, the relativistic effects become very important, and beyond that after that. Okay. So, if you are going to below this wavelength, the relativistic effects are important, but if the wavelengths are much larger, they can be neglected and you can work it out everything essentially. The other thing, okay, that is the reason why the Compton effect is a very important effect to study. Essentially, Compton scattering is a very important study to do essentially. Okay. And there are very many applications in of Compton scattering in astrophysics, in condensed matter, and so many areas essentially. So one should really, in the study of materials and so on. So this is important that you should know, and in astrophysics too. And yeah, so it's a very important task process to study. Now let's look at another important thing, which this kind of scattering happens only in the relativistic case. Okay, this is pair annihilation. A positron and electron come together and annihilate into 2 photons. Okay. So how does this work? So this works by the 2 process essentially. Again, you have E plus. So what we need is E minus. Then there is an E minus, minus. So you have E plus E minus annihilating to give you 2 photons. There is no S channel in this case. So again you will only have U channel and S channel. Okay. So what is happening? Electron coming in and then a positron coming in, both of them annihilate, exchange. Through the exchange of an electron, give you 2 photons essentially. Now question 1, so this is something you should answer and you should know the answer. Why don't we have E plus E minus going to a single photon? Why doesn't annihilation happen to a single photon? Why do you need 2 photons for this process essentially? Why this? So this is also a problem in the assignment. Or a quiz. Okay. So one of people will ask, don't ask them during the tutorial sessions, you try to figure it out yourself essentially. Now I can give you the clue that this is just okay, this is related to some general principles, okay, like conservation of some things essentially, which you already know, and so think about those in those lines essentially. Now you may argue that you should go to a the total procedure should conserve some things, and you can build an argument around it essentially. Now let us look at pair creation. It is just the reverse process of this essentially. So I leave the second thing. Okay, I forgot to work out the amplitude. And in the massless limit, okay, you can, I think ideally you can all work it out in the massless limits without any problems essentially. Now let us look at pair creation. In this case 2 photons come and create an electron positron pair. Now you see the diagrams would be just opposite to this. So, 2 photons come in, okay. This is an electron, and then electron and a positron, okay. Now you can think the other diagram, easily you can figure it out, would be a cross diagram like this, okay. So you can think of a cross diagram like this. So this will be like a E plus, E minus, okay. Where the momenta are exchanged essentially. So you have momentas would be P1, P2, P3, P4, P1, P2, P3, P4. So this would be the T channel, this is the U channel. So these two we can work out the amplitude. The massless limit. So which is essentially m is equal to 0. So okay, good. Now at the okay, last time we were closing at the end essentially what talking about so these are the main things about these are the main 5 to 6 process which said we will look into it in the in QED. Now last time we were saying that there are some symmetry properties which the QED Lagrangian holds, right, essentially. Okay. Now the last time I said there are some general principles of the QED Lagrangian. The QED Lagrangian conserves many properties, essentially many symmetries, and these symmetries have a consequence also on the amplitudes essentially. Say for example, this QED Lagrangian, let us look at the QED Lagrangian. So you have LQED, okay. Now this has several things. It has Lorentz invariance, okay. We can also push our luck and say it is also Poincare invariant, not luck essentially, just push ourselves and say that it is also Poincare invariant. Actually the action is then it is real, it is a scalar, okay. So well and good. So it is Hermitian, so it keeps unitarity intact, and even with interactions which is I e gamma mu, only one interaction, so you have E gamma, okay. These are the only two particles in the theory and they have only one interaction, and this interaction okay, okay, only one interaction, okay, and this invariant interaction is gauge invariant. That means under arbitrary rotation of the electron field, QE psi this under arbitrary phase rotations which are local. Which are local, meaning that means alpha is an position dependent quantity, alpha of x is a position dependent quantity. This entire Lagrangian is invariant. This we have seen it, please check it again. Okay. So, and which this ordinary gauge invariance tells you that which is local gauge invariance tells you that electric charge is conserved at every space time point. Now, there is some subtlety here. Now, Noether's theorem is valid only for global transformations. Like so global baryon number, lepton number, electric charge. So, these are all local or global quantum numbers which appear as a consequence. These are conserved quantities which appear as conserved quantities as a result of continuous symmetry transformations as per Noether's theorem. But in principle, the subtlety is that okay, we are moving beyond global transformations. So, here in QED we have local gauge transformations. So, you cannot really apply you do not have a conserved quantity, you cannot really apply Noether's theorem, but there is always a conserved current and associated with it essentially, and you can build a conserved current, but that is a very special case for the U1 essentially. So, here it appears in here in QED you still have not valid. So, here in QED one still has a conserved quantity in terms of the electric charge, which is some may not be, you cannot equate it with the same thing as a Noether's theorem essentially, conserved quantity which is the electric charge. Finally, the other symmetries, discrete symmetries, such as C, P, T, charge conjugation, which are valid in Dirac's theory also hold true in the presence of QED interactions. Okay. So discrete symmetries such as C, P, T, which are valid typically in free field theory, which is Dirac's theory, okay, are also hold true in the presence of QED interactions, because QED interaction theory is a vectorial theory, it is not a chiral theory, and also it has all these properties that it conserves C, P and T, charge conjugation parity and T, C. It is a simple theory which has a lot of symmetries. So, as a consequence of this discrete symmetries being conserved essentially, so if you are the leading order at the leading order, so what you have is say for example, if you take molar scattering and if you take say for example positrons and do molar scattering with them, it will turn out at the end of the day the cross sections are equal essentially. So, they become equal. So, if you take a difference between these two, if you do an experiment with molar scattering with electrons and then replace the experiment with positrons, the answer is exactly the same, the amplitudes, the cross sections match. So, given that the amplitudes and cross section, and this can be traced back to the conservation laws essentially, which is the charge conjugation. Since the charge conjugation is equivalent, is conserved in QED, you have sigma of E plus going to E plus minus sigma of E minus going to E minus. In QED, this entire thing you can predict it to be 0. Okay. This is because of the discrete symmetry. Okay. This is the okay. So, this is the tree level QED interactions essentially. This we try to cover all possible interactions and some cross sections, some simple process in QED. You should remember this. So, there are these symmetries of Dirac theory which also pass over to QED. So, the interactions are very simple. So, they are not complicated and they conserve parity, they conserve charge conjugation, they conserve chirality and so on, so essentially. Okay. Now, I will stop here, and in the next class what we will do is we will take the scalar version of this theory. Okay. We will take the scalar version of this theory before moving to higher order corrections to the QED, and then look at what are all the possible corrections and what are the differences between these two theories essentially. Okay. I will do this in the next class, and I will stop here essentially. Thank you very much.